In our prior lessons, we used an augmented matrix to represent a system of linear equations. There is a branch of mathematics called linear algebra that deals with matrices in such a way that an algebra of matrices is permitted. This lesson will provide an overview of how matrix algebra is developed. Okay, so the idea is, up to this moment, we've used matrices to solve a system of linear equations. And it turns out there's more than one interpretation of what a matrix can do for us. But in order to get that, we have to understand some more operations or some more things inside a matrix itself. So the goal here is to focus on what a matrix tells us. All right, so the first thing is a matrix is defined as what's called a rectangular array of numbers. So here you see an example. An array of numbers is just an organization type where we've got rows. So we got a row here and a row there, and so we have rows, and we also have something called columns, rows and columns. Okay, now we're going to set up our own matrix here, just to kind of help us understand how these numbers come to play. So we've got some information about groups of individuals. We're asked a question about how much did they think the spending on the federal defense was too high or too low, or I don't know. And so we're going to organize this information into a set of numbers and sort of help us organize this. We've got too high, too low, and no opinion. So I'm going to set up my columns as such. So too high, too low, and no opinion. Get it? No. Okay, anyways. And then underneath that umbrella, we've got males and females. Okay, so then I'm just going to put the numbers in where they are. So 150 males thought the defense was too high. 225 thought it was too low. And 55 had no opinion. 330 females thought it was too high. 115 thought it was too low, and 70 had no opinion. Okay, now but look at what happened. If we take off the title, we're looking at a rectangular array of numbers, in which case each row and each column have some sort of contextual meaning based upon how we got the numbers. Okay, so first thing we're going to do is just practice reading the matrix. So whenever we look at a particular element, so we call it I's and J's, I refers to the row, and J refers to the column. In other words, the first number tells us the row, the second number tells us the column. Okay, so what is element 2, 2? Okay, so I want to go over, there's row 1, there's row 2, there's column 1, there's column 2, so I want to go over to right there to 115. So that's element 2, 2 is 115. Element 1, 3, let me get rid of my arrows here so I can emphasize this. Alright, so 1, 3, the 1 represents the row, and let me switch colors. Alright, the 1 represents the row, and the 3 represents the column. So 1, 2, 3. So we're looking at that position right there. So that would be 55. And then lastly, what is the number 70? Well, here's the number 70, and it happens to be in row 2, and it's in 1, 2, 3, column 3. So it's element 2, 3. A matrix is defined by the number of rows versus columns. If the matrix has the same number of rows and columns, we call it a square matrix. Okay, and so the idea behind defining matrices is we again count rows and columns, and so that refers to the dimensions of a particular matrix. So here's two examples we'll kind of briefly look at. What are the dimensions of this first matrix? Well, counting rows, we get 2 rows, and then counting columns, we get 4. So this is a 2 by 4 matrix. Next example, if we count rows, we have 3 rows, and if we count columns, we have 3 columns. And since we now have a word that describes this, the 3 by 3 matrix, notice the rows and columns match, so this would be an example of a square matrix that we just talked about a second ago. Okay, suppose that A and B represent 2 m by n matrices. Let me kind of pause real quick. M by n means there's a row and a column. I'm not going to tell you if they're the same or not. I'm just going to tell you that there's a matrix, and M and M might be same, they might be different. It's just we have a matrix with rows and columns. There's 2 of them, matrix A and matrix B. We define their sum, A plus B, to be the m by n formed by adding corresponding entries of A to the corresponding entries of B. We define A minus B in a similar fashion. Okay, so the long and short of this is, in order to add 2 matrices together, I have to have corresponding positions to combine them to. So if you think about it in context, we're looking at 2 different data sets that have the same columns and rows, and so each column and row should match up with a corresponding partner. So A plus B means I'm going to take 0 and add it to -1, which is its corresponding position. 1 plus 4, 2 plus 8, and then I'll go down to the second row and do the same trick. So I'll grab all the numbers, so -2 plus -3, 3 plus 5, and 7 plus 6. Okay, and then I just want to simplify each step. So that's -1, 5, 10, -5, 8, and 13. All right, A minus B is defined in a similar fashion. So we take the first number, subtract the second number. First number, subtract the second. And just make sure I've partnered them up correctly. And again, watch signs. So if I have 2 negatives make a positive. So, all right, -2 subtract -3, 3 subtract 5, and 7 subtract 6. And then I just want to simplify that. So that should be 1. 1 minus 4 is -3. 2 minus 8 is -6. -2 subtract to -3. So that's really -2 plus 3. So that's also 1, -2, and then 1. We can also multiply a matrix by a real number. So if K is a real number and A is an m by n matrix, then the matrix Ka is the m by n matrix formed by multiplying each entry of A by K. K is referred to as a scalar, so SCALAR. And the matrix Ka is called a multiple scalar of A, or scalar multiple of A. Okay, in other words, I can multiply a matrix by a constant, by a number, and literally I just go in and multiply each position by that number. Obviously I have to come back and simplify all of this. Okay, so that works out to be 0, 3, 6, negative 6, 3, I'm sorry, negative 3 times 3 is 9, whoops, 3 times 7 is 21. Okay, and so that 0, 3, 6, negative 6, 9, 21 is a scalar multiple of the original matrix A. Just means we multiplied by something to get it. Matrix B, the same thing. So 5 times each number. And then I just need to simplify each position. So negative 5, 20, 40, negative 15, 25, and 30. And we can also, kind of this next part, we can multiply and then subtract. And so in that case, we can multiply first and then subtract the result. So 0 minus a negative 5, 3 minus 20, 6 minus 40, negative 6 subtract negative 15, 9 subtract 25, and 21 subtract 30. And then I just want to go back and simplify all of that. So that would give us 5, negative 17, negative 34. That's negative 6 plus 15. So that would be 9. This would be negative 16 and negative 7. Unlike adding and subtracting matrices, which require the dimensions to match, multiplying two matrices together requires a different set of rules. Okay, so we need to take a second and talk about when we are multiplying matrices, what does that physically mean? Because we know what a scalar product looks like. That's where we just multiply the numbers by another number, and each value in the matrix gets the same product. But what does it mean if I actually physically multiply matrices together? Well, we define a matrix product as a row times in the first column, I'm sorry, a row in the first matrix times the corresponding column. So in a very simple sense, we have a row matrix here, which is a 1 by n matrix, and here we have an n by 1 matrix, so the column matrix. Again, the first number is the row, the second number is the column. And I can multiply this. Let me kind of show you how this looks here. So I am multiplying the two matrices together. Now what I'm looking for to make sure the product is defined is if that inner number matches. And if the inner number matches, the result is going to look like the outer number. So in other words, if I multiply these two things together, I end up with a matrix that looks like a 1 by 1. So that's just a number, one value. Okay. So the process in which a row times a column looks is this sort of last step here. And we end up taking the row from the first times the column of the second, plus the row of the first times the column of the second, just partnering all these rows and columns up. So when you're multiplying matrices together, depending upon how many rows and how many columns you are, you're going to set up something like this, where you're multiplying two numbers together, adding them to another set of numbers. Okay, and so that means that not everything can be multiplied. So adding requires that matrices are of the same dimension, but multiplying not so much. So in order for two matrices to have a what's called a defined product, the rows of the first matrix have to correspond to the columns of the second matrix. Okay, So consider the following three matrices, A, B, and C. What I want to do is I want to go back and find the dimensions first. So the dimensions of A, say 1, 2, so a 2 by 3, it's got 3 columns. Dimensions of B are a 2 by 3 as well. And the dimensions of C, well, we got 1, 2, 3, so 3 columns, and, I'm sorry, 3 rows and 2 columns. I wrote that correctly, said that wrong. So 3 rows and 2 columns, so it's a 3 by 2. Okay, so now what we're going to do is we're just going to play with this for just a second. Can I multiply? I mean, I've got 3 things there. I've got matrix A, B, and C. Are all of the products defined? In other words, can I just multiply them all together and get something else? Well, I'm going to line them up and see what I get. So A times B, so a 2 by 3 times a 2 by 3. Notice the numbers don't match, so it's the product is not defined. I'm going to clarify here, ND in this case is going to equal not defined. In other words, I can't multiply those together, which is kind of weird because I can add them together, but I can't multiply them together. BA is a 2 by 3 times a 2 by 3. Again, the inner numbers don't match, so the product is not defined. AC, so a 2 by 3, and C is a 3 by 2. Okay, so notice the numbers match, and so I'm going to get the outer numbers, so I'm going to get with a 2 by 2 matrix. So I'm going to get a matrix that's smaller as far as the numbers that are in it. CA, so CA is a 3 by 2, and A is a 2 by 3. Okay, notice the numbers match, and so my result is going to look like a 3 by 3. Okay, now let that sort of sit in your head for just a minute there. So if AC it works and CA works, but notice I don't get the same dimensions. A times C is going to be a smaller square matrix, a 2 by 2, but C times A is a larger one, a 3 by 3. So we kind of have to wrap our heads around that one. That's just, it's kind of a weird sounding rule that the way you multiply changes the type of answer you get. Let's look at BC. So BC, B is a 2 by 3. C is a 3 by 2. Okay, now, again, the inner numbers match. So we get a 2 by 2 as a result. And then CB, so C is a 3 by 2, and B is a 2 by 3. Inner numbers match here, and so we end up with a 3 by 3 matrix.